Hey everyone, welcome back to the DSA series. In today's video, we'll tackle an important problem called valid anagram. It's a beginner-friendly question, but packed with key concepts that you'll use in more complex problems. Let's break it down step by step. Let's start with the problem statement. We are giving two strings, S and T, and we need to determine if one string is an anagram of the other. An anagram is a word or phrase formed by rearranging the letters of another, using all the original letters exactly once. So let's take an example. So we have two strings. There is a S string and there is T string. And the output we need is true or false. So for example, listen. Let's assume that S is equals to listen and T is equals to silent. These two words are anagram because they use the exact same letters in different order. Now let's look at a few examples to understand this problem better. Let's take S as anagram and let's take T as negaram. So the output would be true because both strings use the same characters with same frequency. Let's take another example. This time S is equals to rat and T is equals to car. Here the answer would be false because the characters in S and T do not match. Now let's take another example. This time S would be A, just a single letter, and T would be A and B, two letters. The answer would be false because the lengths are different, so they cannot be anagram. It's also important to understand the constraints for this problem. The first constraint says that the length of S and T should be from 1 character to 50,000 characters. And the second constraint says that it will be English letters only, English lower case letters. So these two are the constraints. Let's talk about edge cases. One edge case is of empty string. For example, S is equals to empty string. Also, T is also an empty string. So the output for this strings would be true because there are two empty strings and they are considered anagram since they have no character. Now let's take another example, another edge case. Another edge case of strings of different length. Strings of different length. So let's assume S is equals to A, B and C and T is equals to A, B, C and D. So in that case it would be false because the lengths are different and they cannot be anagram. Let's take another edge case, which is strings with repeating characters. Here we'll take S is equals to A, B and B. Also we'll take T to be A, B and A. Here you see we have 3 B's, 3 A's and we have 2 B. So it is a match. So we'll say that it is true. It's an anagram because the characters and the frequencies match. Now to make things even clearer, let's visualize this with an example. Imagine the input strings as S equals to anagram and T is equals to nagaram. So here, let's break them down. Here we have all the characters that we need. So we have three A's, 1, 2, and 3. We have single n. A is equals to 3, n is equals to 1. We have G is equals to 1. We have R, which is also equals to 1. We have M, which is also equals to 1. So here we have 1n, so that's cut off. We have 3n, 3 A's, so that's also cut off. So we have 1G, that's also cut off. Remaining is 1R. So we have also 1R here, and we have 1M. So that's also covered. So here we can see that both strings contain the same letters in the same frequencies. That's why the output we have is true. Now that we have a clear understanding of the problem, including the examples, constraints, and edge cases, we are ready to explore solutions. We'll first look at simple approach using sorting and then move on to an optimized solution using hashing. Let's get started. So now let's dive into our first solution, which is the brute force approach. In the interview setting, this is the kind of straightforward idea you might start brainstorming to get the conversation rolling. When solving problems, always start by thinking of the simplest solution. Here's one idea. If two strings are anagrams, they will have the exact same characters in the exact same quantities. So what if we sort both strings alphabetically and then compare the sorted results? If they are the same, we return true. Otherwise, we return false. So for the example, here's a step-by-step breakdown of how this idea works. Let's write pseudocode here. This is the pseudocode for our brute force problem. So the first step is to take the input strings S and T. Take input strings S and T. The second is, if the lengths of S and T are not equal, we will return false. Because anagram must have same length. The third step is to sort both strings. Sort both strings. The fourth is to compare the sorted version of S and T. Compare the sorted version of S and T. And the last step, if they match. If they match, we'll return true. Otherwise, we'll return false. So this is our pseudocode for brute force approach. Here is step 2 is critical because strings of different kind, strings of different length can never be anagrams. Let me show you the step 2, which is if the length of s and t are not equal, we return false. So this is a very crucial and critical point. So what we'll do is we will walk through an example. Again, we have used above. Let's take s is equals to anagram, and let's take t is equals to nagaram. First, we check if the length of s and t are the same. So we'll check 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 1, 4, 5, 6, 7. So yes, both of them does have same length. Next, the next step is to sort the strings alphabetically. So S would become A, 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 G, M, N, and R. And T after sorting will also become A, A, G, M, N, R. Now we compare the sorted versions. Since they are identical, we return true. Now let's talk about the time complexity of this approach. First is the sorting step. Sorting step is the most computationally expensive part of this solution. Sorting has a time complexity of big O of n log n, where n is the length of the string. The second thing is comparison. Comparing two strings of length n takes O of n. So we have comparison, which also takes O of n. So the overall complexity is big O of n log n, dominated by the sorting step. The space complexity is also O of n, as we store the sorted version of the strings. So why it's not optimal for large inputs? This approach works well for small strings but can become inefficient for large inputs, especially as the size of n grows close to the constraint, which is 5 times 10 to the power of 4. Sorting is computationally expensive, and there are more efficient ways to solve this problem. But before we optimize, make sure you understand this approach, as it's a great starting point in interviews. Now we have seen the brute force approach. Let's move on to a more efficient approach that avoids sorting. This method uses hashing to count character frequencies, and it works in linear time, much faster than sorting. Let's dive into how this works. Here's the key idea. If two strings are anagrams, each character must appear the exact same number of times in both strings. So instead of sorting, we'll count the characters in one string and then verify those counts against the second string. So let's start by explaining this algorithm and writing pseudocode. First, the first step is to check if the length of s and t are not equal, we'll return false. Now the second step is to create an empty dictionary. We will be naming it count. The third step would be for each character in s. For each character in s, increment its count in dictionary count. Also, our fourth step would be for each character in string t. This time we'll be decrementing. Decrement its count in dictionary count. Also, if any count becomes negative, will return false. And if it doesn't, so the last would be return true if all counts are 0. If the count becomes 0, then return true. So the fourth point, this point is very crucial. If any character counts becomes negative, it means T has more of that character than S. So the strings cannot be anagrams. So let's talk about the efficiency of its approach. The first is character counting. We traverse each string just once, so which takes O of n time, where n is the length of the strings. The second one is hash map operations. Adding or updating a key in the dictionary takes O of 1 time. Since we process each character once, the operations are efficient. The third is the overall complexity. The overall complexity boils down to O of n, which is much faster than the brute force sorting approach, which was O of n log n. The spaced complexity in this time is also O of n because of the hash map. Now that we have a solid understanding of the problem and the approaches, it's time to write the code. We'll be implementing both the brute force solution and the optimal solution. I'll guide you through each step and explain every line in detail so you can fully grasp how it works. Let's start by coding the brute force solution using the sorting approach. Remember, the idea here is to sort both strings and compare them. So we'll start off with def is anagram, which takes in S and T. First, we'll check if length of S is not equal to len of T. If that's the case, we'll return false. Then we'll do sorting. Sorted S equals to sorted, and we'll give the S string. Again, we'll do the same thing with sorted T equals to sorted, and we'll give it T. So it will sort S and T. Our third step is to compare if sorted S is equal sorted T. Then we return true. If that's not the case, we'll say else. We'll return false. That's it. Now let me go over this code line by line and I'll explain what's happening in detail. The first line here, this defines our function is anagram, which takes in two strings S and T and returns a Boolean value of true or false to indicate whether the strings are anagrams. Then what we do here in this line 2 and 3 is we check if the lengths of the strings are the same. If the strings are not equal, we immediately returns false because strings of different lengths cannot be anagrams. Here in these two lines, we use Python's built-in sorted function to sort both strings. Sorted, this function returns a list of characters sorted in ascending orders. Now we have the sorted version of both strings, sorted S and sorted T. In this part of the code, we compared the sorted strings. If they match, it means the original strings are anagrams of each other. So we return true. Otherwise, we return false. Now that we have completed the brute force approach, let's move on to the optimal solution using a hash map. We'll count the frequencies of each character in both strings and compare them. So we'll start off with from collections, import default dict. We'll do def is anagram, which takes in S and T. Again, first we'll check if the lengths of the strings are equal. If len of S is not equal to len of T, we return false. Now we create a dictionary to count the frequency of characters. So count equals to default dict, and we'll pass in int. The third step will be to count the characters in the first string. For every character in S, we add that character inside our count dictionary. Now once that's done, we'll run another for loop, which is for character in T. For each character in T, we now decrement each character from the count dictionary. We also have a if statement here. For if any character goes negative, we'll return false. So for that, if the character in the count dictionary goes below 0, is less than 0, then we'll return false. Lastly, if all the character counts are 0, we will be returning true. Now let me explain line by line. From line 1, we have from collections import default dict. We import the default dict from the collections module. A default dict is a special dictionary where if a key doesn't exist, it automatically initializes it with the default value. Where we give int, it will initialize it with 0. Here we see that just like in the brute force solution, we check if the lengths of S and T are equal. If they are not, we return false immediately. In line 6, we initialize a default dict called count that will store the frequency of each character. The int here ensures that each key starts with the default value of 0. Now let's talk about line 9 and 10. Here we iterate through each character in S. For every character, we increase its count in the count dictionary by 1. Here we iterate through each character of T. For each character, we decrease its count by 1. If the count ever goes negative, it means that T has more occurrences of that character than S. So we immediately return false. Lastly, we return true, as we have successfully completed both loops and the counts are balanced. We return true, indicating that the two strings are anagram. Now that we have seen both solutions implemented, let's quickly summarize the time complexity. For the brute force approach using sorting approach, the time complexity is O of n log n, where n is the length of the string due to the sorting step. The space complexity is O of n because we store the sorted strings. For the optimal solution using hash map approach, the time complexity of the optimal solution is O of n, where n is the length of the strings. We make two passes through the strings, one for counting characters in S and one for updating counts with T. The space complexity is also O of n because we store the counts of each character. Let's quickly recap the key takeaways. First, we explored the two approaches to solving the valid anagram problem, the sorting approach and the hash map approach. In the sorting approach, we first sort both strings and then compare them. If they are identical after sorting, they must be anagrams. This approach is simple but not the most efficient. The time complexity is dominated by the sorting step, which is O of n log n, where n is the length of the strings. The optimal solution uses a hash map dictionary to count the frequency of characters in both strings and then compare these counts. This approach runs in O of n time, where n is the length of the strings, and it uses O of 1 space for the hash map, assuming the alphabet size is constant. It's more efficient because we avoid the sorting step, and we only traverse the strings once. Remember, the choice between sorting and using a hash map depends on the problem constraints. If you need the most efficient solution, go with the hash map approach. But if memory space is a concern, the input size is smaller, sorting would be just fine. That's it for today. We have covered the valid anagram problem, explored both the brute force approach and the optimal approaches, and discussed how to handle edge cases. I hope you found this video helpful. If you enjoyed the content, don't forget to like, share and subscribe to my channel for more DSA tutorials. And as always, feel free to drop any questions or comments below. I'm happy to help. Happy coding, and I'll see you in the next video. Keep practicing and remember, consistent effort leads to success.